You know how a chess AI seems to see the future? Like it can calculate millions of moves in just a few seconds? It feels like some kind of magic, but it's not. It's all about thinking smarter, not harder. So let's pull back the curtain and take a look at the brilliant algorithm that makes it all happen.
To really get why this is so clever, we first have to wrap our heads around the huge problem that any game-playing AI is up against. And it really is a dilemma of just sheer, overwhelming numbers.
So yeah, let's ask the big question right at the start. How on earth does it do it? How does a machine sift through this branching universe of future possibilities to find the perfect move, without just getting completely lost in the chaos?
Well, the starting point for most of these AIs is an algorithm called Minimax. The idea is actually pretty simple. You have the AI, which we'll call the max player because it wants to maximize its score, and its opponent, the min player, wants to do the exact opposite, minimize that score. So the AI maps out every single possible move and countermove, looking for the one path that gives it the best possible result, assuming its opponent plays perfectly.
But here's the big, hairy monster of a problem. In computer science, we talk about time complexity, and for Minimax, it is brutal. B here is the branching factor. That's just the number of possible moves you can make each turn. And D is the depth, or how many turns you're looking ahead. This number gets astronomically large, incredibly fast. We're talking trying to look just a few moves ahead in chess could take longer than the age of the universe, seriously. This is the villain of our story.
So, brute force clearly isn't going to cut it. We need a more elegant solution. A way to get the same perfect result without doing all that pointless work. We need a smarter way to play.
And that brings us to the core aha moment. What if you could know with 100% certainty that an entire branch of future moves was completely useless to even look at? What if you could just ignore it?
This, my friends, is Alpha-Beta Pruning. It's not a totally different algorithm. Think of it more like Minimax 2.0. It's a much smarter version that finds the exact same perfect move, but it gets there by intelligently ignoring huge sections of the game that it realizes can't possibly change the final decision.
So how does it know what to cut? Well, the magic comes from two little values the algorithm keeps track of as it explores the game. Let's meet alpha and beta. Okay, think of alpha as the max player's score to beat. It represents the best, the highest value that max is already guaranteed to get so far. Beta is the same thing but for the min player. It's the lowest score that min can force. The whole thing becomes this tug of war. Max is always trying to push its alpha value higher and higher, while min is trying to drag its beta value lower and lower.
Now, theory is one thing, but seeing this in action is where it really clicks. So let's walk through a simple game tree and watch the algorithm work its magic.
So the algorithm dives down the very first path it can, all the way to the end. It finds two possible outcomes, a 3 and a 4. The node right above them belongs to the min player, whose entire job is to pick the smallest value. So, easy choice, min picks 3. That 3 gets passed up the chain to the max player. Max looks at that and immediately sets its alpha value to 3. This is a promise. It means Max now knows, okay, I have a path that can guarantee me a score of at least 3.
All right, now the algorithm backs up and moves over to explore the next branch. It dives down and immediately finds a possible outcome with a value of 2. Now pay close attention, because what happens when this 2 gets passed up to its min player parent is where the magic begins.
And this is the moment of genius. The 9 player on this new branch sees that 2 and knows it can force a score of 2 or maybe even something lower. But hang on, Max from a level above is already thinking, wait a second, I already have a guaranteed way to get a 3. Why on earth would I ever make a move that allows my opponent to force me into a 2?
It wouldn't. It makes no sense. The condition is met. The min player's best possible outcome on this path, which is 2 or less, is worse than what the max player is already guaranteed, which is 3 or more. So, snip, we prune. We don't even have to look at the other nodes on this branch. We don't care what they are. They are totally irrelevant. And this process just continues. Let's say the algorithm moves on, explores a completely new section of the tree. Down this new path, it finds a situation where max can guarantee a score of at least 7. So the local alpha for this section becomes 7.
But now, look at the parent min node. That min player remembers the very first branch we explored. It knows it can force Max into a situation that results in a score of just 3. So when this new path offers Max a shiny score of 7, the min player basically says, nope, not gonna happen, I'm not letting you go there. I'll stick to the path that limits you to 3.
And boom, that's the second type of prune. Max's potential score here, an alpha of 7 or higher, is already way better than the score min can force somewhere else, a beta of 3 or lower. The min player will never ever choose this path. And so, the entire rest of this whole section can be pruned away. We just saved a massive amount of computation.
By just repeating this simple logic over and over, the algorithm carves away these huge portions of the search space. So what does this actually mean in terms of performance? What's the real payoff here?
Well, the difference is just dramatic. Minimax is a completist. It feels like it has to check every single possibility every single time. Alpha-Beta is a strategist. It only looks at what could possibly change the outcome, and it intelligently ignores everything else.
Let's put some numbers to that. Remember our villain, b to the power of d? In the best-case scenario, Alpha-Beta's time complexity is effectively the square root of Minimax's. That's a huge deal. It means that with the same amount of computing power, you can look twice as deep into the future. If Minimax had to check 1,000,000 nodes, Alpha-Beta might only have to check 1,000. This is a monumental improvement.
And this is exactly why it matters. This efficiency is the difference between an AI that can think 2 moves ahead and one that could think 10 moves ahead. It allows the machine to search so much deeper into the future in the same amount of time, making it an exponentially more powerful opponent.
So, as we wrap up, it leaves us with a pretty fascinating thought. This algorithm's power doesn't come from processing more information, but from knowing what information to strategically ignore. What could that principle mean for the future of intelligence, both artificial and maybe even our own?